Shivraj sir, please let us know, when we are live.
Yeah, yes. Okay, hello everyone. Hello everyone. Let's start today's session. Yesterday we had revised the topics. We can say like tree, and we also did learn some concepts about the tree data structure and the backtracking as well. So me till now we have what we have revised. What we have done is stack, cube. We have also seen recursion. We have also seen dynamic. We have also seen a little bit about backtracking. We have also seen queue. We have also seen tree data structures. So all those data structures, what we have done, what we have learned till now, are very important for us. And you can also revise from the videos in the YouTube channel. So now today we will be starting with a new topic. The topic is so today's topic will be graph, right? So whenever we need to understand why graph is used and what graph data structure is all about. First, let's understand about the graph data structure. Then we will implement its algorithm also practically, and then we will go more further towards understanding the graph. Right. So whenever you see any application, any application, any online application, which is using the networks, like which is working like in a form of network. Let's say you can say social media, all the social media networks like LinkedIn. You must have heard about the LinkedIn, right? So each and every person is connected to so many person, right? And you get the invitation, right? You get the invitation from other person to join, right? So LinkedIn all other kind of application LinkedIn is there that LinkedIn also uses the concept of graphs, right? So any application which is involving the mechanism of networking, like connecting people, like connecting nodes, connecting entities, these sort of all application include, or I can say, contain the graph mechanism. So the graph, basic data structure, basically covers two important crucial parts. The graph basically contains two things we can do. This is this is called node, or you can say vertex, right? And the line joining these two nodes or vertex you can say is edge. This is how we can simplify the graph. Graph is a collection of nodes and edges, right? At the same time, you can also call the nodes as vertices, right? So you can simply like use the graph. You can simply sum the graph like this: collection of nodes and edges, right? So you will see so many graphs like this. So like what I can see over here, like this is also graph. This is also a graph. This graph is with cycle. This graph is with cycle. This is without cycle, right? These are the basically graph that we see. Just a second. Right. One more thing we used to see, that is weight. What I can see is the weight. Weight is the weight given to the edge basically. Is- For example, I've given this weight as I given this edge a weight as 5, is 10, then 15, 20, 35, and all. Right. So this is what basically weight. So this is called weighted graph, right? Why weighted graph? Because each and every edge is given some weight. Right? Each and every weight, because each and every edge has been given a weight. That's why it is called weighted graph. Why weighted graph? Because it's been given a weight. As simple as that. Hope so it is clear to you. So we have seen the weighted graph also, and you can say this is unweighted graph. Unweighted graph, and this is weighted graph, right? This is slight different. One more thing we see that we can also say this is a directed graph. If the directions are given, let's say the nodes are A, B, and C, D. This is called directed graph. From A to B we can go, but from B to A we cannot go, right? This is called directed graph. And earlier what we have seen, if the directions are not there, right? The directions are not given, we can simply say it is an undirected graph. Clear? So we have seen weighted, unweighted, directed, and undirected graph also. The last one is we are just checking, everyone guys, we are just checking the types of graph. Right? Another one is connected. This is, you can say, the connected graph. This is, you can say, this is, you can say, disconnected graph. This, you can say, is a disconnected. Like, right? One more thing. Okay. So I would like to tell you one more thing, that if we have to if we have to implement, like if we have to implement the graph in Java, suppose I want to implement the graph in the Java, then I have to use the generic class, the base class, you can say, right? And I have to create a create of object of generic class as well. So I can simply write like this: base class, whatever I will use it, base type, basically parameter type. Don't worry, I will take the example also. I'm just explaining the syntax how you will use the graph. See, there is no specific class for the graph, right? Earlier we have seen, right? Earlier we have seen for the stack, we have seen for the tree, we have seen for the queue. Tree also, you can say, is implemented with the help of list also only. So we have seen tree specific class for stack, we have seen specific class for queue also, but there is no specific class for the graph as well. Because graph is always represented in form of two things, right? Either you can represent in the computer memory, you can say in the computer memory, you can represent graph in two ways. First one is adjacency, list. Second one is adjacency matrix. These are the two ways. These are the two ways by which you can represent the graph, right? In computer memory, you can simply sorry. You can say sorry. So you can represent a graph in form of adjacency matrix and adjacency list, right? Right. So these are the few ways by which you can represent. I'll tell you how to like represent a graph in form of adjacency list and adjacency matrix. Don't worry. So I want so now this is the parameter type. Here we mentioned the parameter type. Then we will make an object, new keyword, base type, parameter type. Here also we will write the same and function and close it. So this is how we will declare uh, this is the syntax of declaring the basically a graph using any generic class. And what generic class we will use, I will show you in the Java. I'm just showing the example, right? Example, right? So we will implement this graph in the Java itself. But before this, I would like to we have to understand what basically adjacency list and adjacency matrix. Because before we can't just start without understanding these two things, right? Right. So let's move further. Suppose we are given with the graph like this. We are given with the graph. Let's say we are given with the graph this. Right. Right. Let's say these are the vertices are A, B, C, D, and E. Right. So how will I show this? First of all, I will make the adjacency matrix. First of all, we will make the adjacency matrix. So how will I make the matrix? So what I'll do, I will write the simply vertex name A, B, C, D. Same I will write over here A, B, C, D. So this adjacency matrix and adjacency list, how do you define this? Basically, see, you simply check which vertex is adjacent to which vertex, right? Suppose A is directly connected to B and directly connected to C. So A is just adjacent to B and E. I can say is adjacent to D is adjacent to E and C. So similar, this is how you do. So A is not but adjacent to A itself. A is adjacent to B and E also, right? And A is also adjacent to E. The remaining will be zero. Same goes here. Like B is also adjacent to B is also adjacent to A and C. Other vertices R will be zero. So this is how you can simply make an adjacency matrix, right? And what about the adjacency list? Yes. What about the adjacency list? The adjacency list will work like this. You simply write A. It will work like a you can say simply linked list also. C, D, and so on, right? So A is adjacent to which B and E. B and A. Simply it will connect to B and C. This is on null. Why? Because there is no connection further. And B is connected to A. You will say and C. A was not connected. A was connected to A, B and and A B is connected to A and C only. Right? Right. So this is the representation of my adjacency list. So the adjacency list is like this. Adjacency metric is this. These are the ways. These are the ways by which we can represent a graph in computer memory, right? So these are the basically computer representation. How computer stores a graph, right? That like it doesn't matter how do you understand the graph, but you need to remember how do you represent how computer basically how computer memory represents how computer memory stores the graph, right? These are the two ways basically are used to represent the graphs in the computer memory, right? There are some other ways also. Orthogonal list and some other lists are there, but they are not of use right now. So I think we have got this two list. What how do we use this list, right? Further, we will also know. I will also like to know about the traversals in graph. I will also like to know about the traversal in the graph, and we will also see the BFS and DFS, which we were discussing earlier also. That is quite important, right, for us, right? So now try to understand what basically we can do. We will learn, right? So now let me tell you. Okay, just a second. Let me see. So now let me take an example of implementing a graph in the Java. So I have made a class. I have taken a class. So what I'm doing, I'm just making a program to implement graph in Java, right? So let's see how do we implement, right? Let's see how do we implement. So I have taken this graph underscore example, right? Wait. Let's okay. So let's start. Let's implement this graph in Java. Meanwhile, I will be explaining the code also while coding, right? Don't worry. So let's import the util package because so many support is there from the util package itself, and if we don't know how many support we require, then just simply import all the things in the util package in the Java. So suppose I import. So now I imported the Java util package. Now let's start with the class. So I define a class here itself like this, right? So here I have to start like this. Graph example. Let me define a type T. So let's create an object of map class which will be storing the edges of the graph, right? So what we will do, we will just create an object of the map class, because map is like something, what map is like something set or something list which can store the data. So we'll create an object of map class here that will store the edges of the graph, right? So what I'll do, let me write over here for the you also. Create object of map class to store the edges of graph, right? And this is how, like, we can simply see. So like, let me make a make. Let's make the make private also. So in the map, what we mentioned is the key and the value form. The value is list, you can say. In list, you have mentioned the type T. Let's make an object as named as map. And new, always the map class always extends the references the hash map, right? Because we implement the map with the help of, we reference the map, we extend the map with the help of hash map, right? Right. So this is how, like, we can use the map, and we can also declare this public as well. No issue in this. Right. So what we have done till now, we have made, so what sorry we have made up, we have just generated an object of map class so that we can store the edges of the graph, right? So what I've written, we have just taken map, a list having the P is a type, a list, right? And map is the map, small map is an object, and we have just referenced the new hash map. Sorry, we have just referenced the hash map class to create the map set, right? So now let's make a method who can add the vertices, right? We have created an object to store the edges, but what about the vertices? So let's make a method, a function. Let's take a function who can easily, like, add the vertices to the graph, suppose, right? Let me take a method. Let's say the method is add vertex. That is add vertex. Right? Let's make a method add vertex. Right? Right? Okay. So so what we have done, we have just making a method. Let me comment also so that you can easily remember the code. Every time remember, whenever you are making a good program, whenever you're making a little bit long program, always use the commenting practice so that you can easily understand, you can easily remember what you are doing, right? Right. So you are taking this to method to add. You can say method to add new vertex to the graph. So we are creating this method to create the new vertex into the graph, right? Sorry, sorry. Map dot put. So we are using the puts method. We have already seen we use the puts method to, put method. Already seen we use the put method to insert something in the map, right? In the list, you can say. So S is the object we have made. Here S is the object of this T, right? So as by this object we will, by this object, what we will do, we will add the vertices this to the list. So what we'll say, we will say create a new linked list, because because we are adding, because what we are doing, we are adding see, because what we are adding a list, because we are adding the vertices to the list, that's why we are creating an object of new linked list, right? Here we are passing the key is T, right? And then, right, so in the P is just the key we have passed. This is the list we are creating with this key P, and this is a map is an object. Then with the help of new hash map, we are creating this list, right, of map, right, named as map. So now what we have, now we are creating one more list to add the vertex, right? So what we're doing, we are just using map and dot put method. So put method used to add the new data element to the map. So as is the object we have passed of this key, and then we have created a new linked list, right? We're passing the key here T, right? So that we can simply add this vertices with this new list we are creating, right? So this method will simply, whenever we will call this method, right, this add vertex, right? Whenever we will call this add vertex, right, we will simply be adding the vertices to the list, right? I'm making another method, right, which adds an edge between source and destination. Source and destination means, let me explain you. See, what we are doing. Basically, we are creating a map class, a map, a list to store edges, We are creating a list to store vertices. Now again we have to maintain, we have to add, suppose these are the vertices, we have to add an edges between these vertices. We have to add edges between these vertices. So to add the edges between the vertices, I will be taking a new method called as, you can say, public void add new edge. You can give any name to the method. I've just taken here add new edge, right, so that I can remember it. Always in the coding, for the coding practice, it is very useful. Whenever you are using the terms, whenever you are using the identifiers, right? So identifiers is what, the name you are giving to a function, to a variable or a class. So you should use those sort of names which actually resemble those its functionality, right? Like here, what, why I'm making this method, to add a new edge, right? To add a new edge between source to destination, you can say, or between the vertices, right? But same thing, my method is also conveying me the same, that this method is about adding a new edge between the vertices. So it is always good in the coding practices if you give that, if you use those sort of identifier which actually resemble the functionality also, and which actually make you understand easy, like make you understand easy that why this method has been used. Although we are also using comments also, so that you can easily can explain understand. So why we using, to add an edge between, you can say, source and destination vertex, you can say. So add an edge. So why we are using this method, the function, to add, to add the source and to add the edge between source and vertex, source and destination vertices, right? So right, like this, great. So we are passing a t, we are passing a source vertex. What a source vertex will be, we are taking t, we are passing a destination, we are taking an object destination vertex. You can give any name here, you can give any name here, like I have used source and destination, you can use any name, no issue there. Then I have to check whether it is now a source or destination. I am adding an edge from source to destination. Again I have to check whether it is bidirectional or not. I have to check whether it's a bidirectional or not. Then how will I check? I'm taking a boolean variable name as bidirectional. Like, so you need to understand like why I've taken this boolean variable. I have just to check whether my edge is bidirectional or not. Right? Just to sake of this, I've used this bidirectional. I've taken this bidirectional boolean variable just to ensure whether my edge is bidirectional or not. Right? So like this is how we've started. Now let me tell you, if I will check whether my map, whether my map, who's containing the like key source vertex or not, right? I will check if my map contains source vertex or not, right? So if it is not, I will check simply right if map dot contains, because map is a list. So with the help of contains method, I can see easily check, right? So map will always maintain the data in form of key and value, right? Key and value. So I'll checking whether my map contains key or source. If it does not contain, what simply I write, I will add. I will call this function add vertex. I will simply call this add vertex method here. So what basically I'm doing here? I'm just checking if the map does not contain the source vertex. I will simply add the vertex named as source add to the list. I will simply add source vertex. I simply add a vertex named as source to the vertex list, right? Again, I will check if my map right does not contain. Again, I will check if my does not contain what destination. We will check destination, right? The variable which we have choose, right? Again, I will choose if my map doesn't contain destination, right? Again, I will check if my map, right? What I'll do, I'll simply write again call this method add vertex and simply mention which vertex I need to add destination. So that's what we have done. यहाँ पे हमने चेक करा अगर सोर्स नहीं है सोर्स ऐड कर दूंगा लिस्ट में सोर्स वर्टेक्स ऐड कर दूंगा अगर if we are not having the destination vertex I will simply add the destination vertex to the list, right? To the list, right? This is what I have done till now. Now I'm done with the source and destination. I got the source and destination. What I'll do, मैंने source and destination ऐड कर दिया है. What I will do now, अब map से I will find the source. Sorry. Now I will get the source from the map. How? I simply write map dot get source. Get method to right. Get method is used to get the object. Yes. So what object I need to get is this source vertex. Source vertex, and then I will add this to destination. Simply again, please try to understand. Here, this add vertex method is adding the vertex to the list to the map exactly, right? Here, the add new edge is doing what? It is simply adding. It is simply connecting the source and destination vertices. You can say two vertices and the line joining these two vertices. What I'm doing, and the boolean variable. I will tell you why I've taken this boolean variable because it also plays some quite role in some of the cases, important role in some of the cases. So first of all, checking if it is the source vertex is not there, I'll simply add to the map. If the destination vertex is not there, I will add to the map, and now I'll get the source to add to the destination. I'll add the source to the destination. From the map, I'll get the source vertex and I'll just add it to the destination vertex. Now I have to check. Whether my map is bidirectional or not. Whether my map is bidirectional or not. So let me tell you how. This is source. This is destination. So bi-directional, if it is if it is unidirectional, then simply source will be get connected to the destination. But if it is bi-directional, then again I have to connect the destination to source also. What I am doing here, I'm just simply connecting. I'm just simply connecting the source to the destination, considering that it is unidirectional. But now I have to check whether it is bi-directional. If it is bi-directional, then again, if it is bi-directional, then again, what I have to do? Now I will check. Right. Now I will check whether it is bidirectional or not. Right. Sorry. Now I will check whether my map is bidirectional or not. So I will check whether by right. I will simply check if once I added the destination to the source, then I will check whether it is bidirectional or not. Right. It is bidirectional. Or not. If it is bidirectional, then what I will do? I will simply write map. The same thing I will repeat here. You can simply write. What I will do? I will just change the source and destination. Here you will get the destination. Here you will get the destination, and here you will get the source. As simple as that, right? So I think this is very easily like I think this is like I think you will be getting this that first we are adding the source to destination, and then we are checking whether it is bidirectional or not. If it is bidirectional, if it is bidirectional, then I'm adding the destination to the source, right? The same method which we have done here, right? Might say checking the condition, right? Hopefully it is clear to you, right? Right. So over this add in we have done with this method. Which method? We add new edge. So we are done with this add new edge method, right? Now we have to create. Now we have to count how many vertices are there in the graph. You can simply count also, right? You can easily count what are the number of vertices are there, right? So you counting the you can say counting the vertices, right? You can say counting the vertices, right? So let's count. Let's start and let's make a program to count the vertices, right? You can simply route system.out. You can simply print the vertices, right? Let's make a method also for the forget to mention. So say like you can use the count vertices, right? So I like to count them. Let's say total vertices equal to map dot key set. So when you have to find the count in the map key, whenever you have to find the set, sorry, whenever we find the length of the key set in a map, whenever you have to find length of a key set in a map, you can simply use size method. I think we have used earlier also in a few days ago. So size method, you can simply find the size of the key set, right? So this is a simple thing that's a simple method you can easily use to find the to count the total vertices, right? Right. Simply similarly, we can also count the number of edges also. Right. Just have to check pass a boolean variable also because boolean why? See We will count the edges on the basis of whether it's a unidirectional or bidirectional, right? So I have to check bidirectional also. So I'm taking a boolean variable again. Bidirectional, yes, right? I'm passing a variable bidirectional also here. Let's take a variable int. Let's take a variable int count, right? So count, we are taking a count variable to store the number of edges, right? So I'm taking a variable count. You can take any variable, whatever you want, right? So now I will run. Now we will use a loop to iterate through the edges, and so that we can count it. Each time we iterate through an edge, the value of count will be increased, right? Let's see how we do this. Simply count the edges. So I've taken a key, right? B is an object of the key, and then I'm taking map, and then counting the map and key set, right? In the key set, I'm just with the help of key set in the map. With the help of key set, I will be checking key value. Basically, I will be checking the key values so that we can iterate through the edges, right? And I will write simply count equals to count plus map. In the map, what we are getting, just getting the size of the vertices, right? So we are getting the vertices in the list, and then we are getting size, right? We are getting size, right? So and we are just getting the size, right? Now I will check whether it's bidirectional or not, right? I will simply add if it is bidirectional, right? I will simply check if it is bidirectional. Then the count will be divided by 2, because if it is bidirectional, then same edge is repeated 2 times. That's why we are decreasing the count by 2, right? I think hopefully you are getting this, right? Now, so I will simply route the total edges. First, count you can say, right? So total edges are count. You can simply write total edges equal to count. So the edges you have count, right? So we are done with this method also. Where what we have done, where we have just seen how we can simply check. We can simply count the number of edges. Now let's go further. Right? Sorry. Let me take a water break. Just 2 minutes. Okay. Now we will check. We can also check that whether a graph has vertex or not. We can also check whether a graph has vertex or not. So I can simply write like void. Simply write contains. What contains? It can contain vertex or not. It can be vertex or not. Here we have passed the key and then now object s. You can see value or you can say sorry as an object over here. So object will type simply without a comma, right? So I will simply check whether our graph contains keys or not, right? If map dot contains key. Right. So I will simply check if our map contains key, right? If our map contains key, then I can simply say wait a second. What is showing here? A map that contain function contain function in the passing the object. Okay, it's fine. Right. System dot println. Why we will check whether it is contains whether it contains the edge is whether it contains the vertex or not. Right. So I simply write the graph has total vertices. Graph has vertices. I simply write graph as vertices equal to, you can say, you can simply write right. I can simply check whether the graph has vertices as right. So this is the I can show that the graph has the vertex as right. If the graph has this vertex, the graph has vertex or not, right? We can simply check. And if it's not the case, if it's not the case, simply write else. And I will write graph does not contain again text. So I'm just checking whether a graph has a vertex or not. I'm just checking whether a graph has a vertex or not with the help of this function. If I'm checking if it contains a graph vertex, we can simply mention. If it does not contain, we can simply mention over there. Right? Clear? I think it is clear to everyone. And we are done with this method. Right? Now same method I will do to check. Same we have checked. We have made the method for checking the vertex whether a vertex whether vertex is there in whether a graph has vertex or not. Similarly, I'll check whether I check a graph has edge or not. Right? Right. So I'll take same. I can write contains edge. Right. I'll pass to parameter. I'll pass the method. First one you can just source as or source, and the second one is second objective. So I've taken so for source, D for destination to make you understand that an edge will be connected from source to destination, right? So as and D we have taken two parameters that represent source vertex and the destination vertex, right? So in the contents edge, I will check if again I will check whether my graph is edge or not. So I will simply check if our map. I'll pass the object as that is I'll pass the list dot contains sorry I'll pass the source and destination. So I'll just check whether my map contains a source and destination. Then I can simply write graph is having an edge from source to destination from wait. You can simply write this to destination. So I'm just simply writing the graph is having edge from source to destination, right? I believe you have understood this. Right? I'm just keeping it easy. I'm just keeping it. The graph is having an edge from source to destination, right? I'm just simply writing it. Okay. And if it is not the case, then what we will see? If map does not contain source or destination, we will simply write no edge. You can say whatever you write. No edge is there between source. You can say simply right. So to destination. Right? No edge is there between source to destination. Right? Okay, right. No edge is there between source to destination. Right? Now we have done. We've add the edges. We have add the vertices also. We have checked the vertex edges if they are not of a graph. We have also checked. We have used this method till now. Now I have already told you that we can always represent graph in form of adjacency list. Matrix you can say. So we will be representing the graph in that form of adjacency list because computer memory also represent the same, right? So let's print the graph in adjacency list, right? Let's print the graph so adjacency list, right? This method is complete. Now you can say showing the adjacency list in form of graph. Right? You can write any command for according to your feasibility, like according to your understanding. Right? So here what I'll do, I'll just override the string to method, right? So that I can modify this string, right? Because string is immutable, right? String builder is immutable, right? So what I'll do, string, right? So I'm converting my string to string, so just to for us to modify, right? I'm taking a method. I'm taking a method, right? So that I can simply we can just print the adjacent list of the vertices. Right. So I will then also write. I was using over annotation. I'm just using annotation override because I'm overriding the string method to string method of string builder class, right? So that I can so that I can modify according to our requirement, right? So I'm making an object of string builder here. I'm making an object of string builder. Let's say b sb new, right? So I'm making an object of string builder sb and new string builder for. So right, I'm using the for each loop for getting the vertices, for printing the vertices, right? So here I will do what I'll do, printing the vertices. I can say printing the vertices, right? So what I'll do, I will use the, we can simply use for each loop. It will be, I'll take an object w, let's say, map, or we use get method to get the vertices, right? always use that method to get the vertices, get the elements of the map, right? So I will use this builder dot append method, right? Append method. What I'm using, I'm appending the vertices to the string. I'm appending the vertices to the string. So what object we have taken here? We have taken object of W. So whatever object by this object I can access the vertices, right? So I'm just adding these vertices to string, right? And vertices to string. Here what I'm just first adding the I'm appending the vertices to the string, right? Whatever vertices I'm getting, I'm just appending this, right? Clear? At last I'm using the null character so that to declare the terminate, to declare the termination. And last I'm adding an null character, what is the null character, right? To terminate this. Okay. So we have taken a string builder object, then we have make a and we have make a map function, right? I think I've forgotten something. We have made a we have like it. We have been iterating to the vertices, but I forgot to use to iterate over the edges also because first I have to iterate through the like edges. First I have to iterate over the keys. Then from that those keys I have to iterate through the vertices. So I just forgot to iterate over the keys. Let's say let's actually I have to use one more loop. Then only I can iterate over the keys. Then after that I can only access the you can say vertices. Right. Right. So I will just use a key the list which is it can. And I will declare a v as an object. And then I will map key set. Right. Why I'm using this? Please try to understand. Inside the you can say this will come inside this because see let me explain. Don't worry. See, first we are what we are doing. We are just like so here what we are doing here basically that we are iterating over the keys. So we are iterating over the keys. Why? Because we need to access the vertices with the help of keys itself. So first we will go through the keys and then we will go to the vertices, right? Right. So we are just iterating over the keys with the help of this list key and the object v to the map with the help of key set function. Then what I'll do, I will simply append. I will simply append. I will use the builder dot append method. I will use the builder dot append method to add the vertices to the string, right? Right. Here then just what I'm doing, I'm just appending the vertices to the string, right? What we have declared a string, right? We have declared an object builder of string builder. So in this through this object builder, through this object builder, what I'm doing, I'm just simply adding, I'm simply iterating over the keys, right? And I'm appending the vertices to the string, right? Now I've added the vertices. Now what I'll do, iterating. Now what I'm doing, getting the vertices. Now I iterated to the keys. Now I will get the vertices, right? This will come like this. right? So I'll say take an object mapped on get b, right? We are getting the vertices. Then we are just simply we have what I've done already appended the right. This I've already appended the vertices all the remaining. I'm just getting the vertices by appending to the string, right? Now let's move the at last I'm adding the null character to the string. And what I'll return this for loop is finished. Sorry, I took over a bit. Then the way we return, what I'll return, I will just return the builder dot we're done with this toString method also. We're done with the toString method also. We have closed the in for loop, we have closed the outer for loop and we have created close the method also. Then I will close this class also. We are done with this class. We are done with this class, right? Because now I'll create a class in which we can implement the driver code. Basically, the code which drives the upper code, right? So driver code, let's write the driver code also. Let's take a class. Class. So this is the main class we have taken. I can take the graph example. Wait. Right. Because I'm declaring the main method in this class, so I have to declare this class as well, right? So simply write this class as like graph example. You can say. Graph one you can say. And let's make a class. Let's then make a class in which we can declare, or we will declare the driver code with the help of main method also. Graph. So I'm the object. I'm making an object of this graph example. Yes, the graph class, graph one we have taken over here. Right. So I'm making an object of graph. Let's say G. You can say now I think we have taken graph one, right? Yes, we have taken graph one class. So I'm making this object of this graph one class here over here, right? So we have made a graph of G object of graph one class here, right? So G is the object of graph one class. You can say, and I'm simply add edges, right? To the graph. So we'll simply add the edges to the graph. Here we have created the class of the object of the graph, one class we have declared above, and named as G. With the help of G, we will add. Right? So, see, we will pass two values. We will pass two values. Add x, we will pass two value, right? Now check. We will pass two. We'll pass source, destination, and boolean also, right? And we can easily pass 1, 2, and it is bidirectional, right? Source, destination, bidirectional, right? Let me copy paste. Hmm. So suppose from one vertex, let's say from 1 to 2, 3 also connected. 2 to 4 is also connected. Let's say you can declare any. That's false. Let's say this is false. Let's say you can pass any value, right? This is quite interesting. I'm just making random. Any graph can be drawn. I think this is enough sufficient for us. We are just adding, right? The edges. Now we have added. Till now we have added. Now let's see how we print this graph. I made the graph. We have made so many methods, right? Now what I'll do? I'll just simply print this list. Sorry, I'll just simply print this graph with the help of agency list, right? Let's do it. I want the solution to come to the next line, so we can simply add an x so that the solution come to the next line. Right? What object we have done? We have taken object G to string. So we will print the graph to the string. Right? You can simply count the number of vertices also. What you can send? Simply G dot count vertices, right? Count the number of edges also. We have made the method. Count edges also, right? You have to pass the edge, boolean because we saw we have passed this by we have passed this in this you can say edges method. We just pass the boolean variable, right, to check whether it is our edge is bidirectional or not. Here also we are passing a boolean value, that's true or false. You can whatever you can pass, right? You can simply check whether an edge is present or not, right? Right. We are just implementing all those methods which we have declared above, right? We are just checking all those methods which we have defined above, right? Okay. So now, sorry. No, sorry. Okay, like this. Let me mention what we are doing. Now check what is there. So I'm checking whether vector is present or not, right? How will I check? G dot G dot content. I'll pass any vertex, let's say 2. So I'll check whether vertex 2 is there or not. Right, and you can simply check, then copy paste this. You can check as many as you want, right? Yes. Now I'm checking whether I'll check whether edge is present or not. And to pass source relaxation, let's see 1 to 2, right? We can simply check whether there is edge or not. Let's just so we're just checking whether it is having edge or not, right? So let's start from the beginning program. Let's run it. There might be some error. There can be some error. Don't worry. We'll just check it. Wait. No, the office is public. Finding okay, don't worry. Wait. It should not be public, right? We are just getting cannot find a variable builder. Just a second. Not an issue. We'll just check it. Oh, sorry. We have used the variable SB. We have used the object SB and we have used that we are writing builder. I think that's fine for us. It works. It will work for us. Just a second. Let's see. Okay. Extra package. That's just, I think everything is fine. So we have just seen this program problem. and I'll show the output also. Meanwhile, it is having some issue. Don't worry, I'll tell you the output out also. And we have to run this method also. Don't worry. So we've just implemented the graph with Java, which is like quite tricky as well, and we need to remember so many things while we are like implementing the data sets like Java, like graph tree, like because so many complexities are there. And you will simply come to know once you do a lot of practice. Because with the practice, you will know the flow, you will know the terms, how you will use it, and how you will implement this, right? Yeah. Let's take a 2 minute break. Let's continue, then continue, next continue. We will start now. Now we will start. Now graph traversal. Graph traversal. BFS and DFS. Just give me 2 minutes. So let's start again. Let's come to the graph traversal part. Like, sorry, excuse me. So graph traversal. Let's start with the BFS and DFS. Excuse me. So BFS is basically breadth first search and DFS is depth first search. So we use the graph traversal to visit the node, and there are two different ways to visit a node of the graph. So first one is the BFS. BFS is basically breadth first search and DFS is depth first search. Both have different ways of searching, or sorry, both have the different ways of traversing the nodes in a graph. And we'll see this how, right? How we will do this, right? Like, so let's start this. Yes, I do this. How, let's see how BFS DFS works. Suppose I am taking a graph, right? I am drawing a graph. And after BFS and DFS, right? So I'm having a graph, right? This is A, this is B, D, this is E. Right? This is A, B, C, and D. These are the vertices, and we are connected now with the edges, right? So once suppose if I start with the depth first search, right? Sorry, breadth first search, BFS. And how will I traverse? Let me tell you. First, I will start with the suppose I start with the vertex A. So so in the breadth first search basically we use depth first search, we use the other data structure, and breadth first search basically use the Q data structure, right? So whenever you like traverse a graph, there is a like a common method that is breadth first search, right? So in this way, we basically start the traversal from the source node and start visiting its neighbor nodes, right? At the same level, you can say, right? Or you can in the short form also you can say that it traverses horizontally, right? And covers all the vertices of the current layer, right? Current level you can say, and then we perform to the next level. For example, we start with the source vertex A, right? So we will cover. We have visited this. Now we have visited this vertex. We will cover all the vertices. Source vertex is this. This is the it is its neighboring vertex. We have visited this. Now this vertex, the vertex C, neighboring vertex. Now this level is complete. Then this level. So what was the flow? A, B, C, D, E. It was the flow of the traversing of the VFS, right? Right. So now, yes. So now we have done, like we have understood what BFS is. Let's try to understand DFS also. Let's now try to understand the DFS. DFS, as its name suggests, is depth first search, right? Depth first search is used in the backtracking also. Yesterday, I gave you the example also. Like we use the depth first search for the backtracking concept also. Basically, in this also we start with the initial node and searches in the depth until we find our goal node, right? Our our resulted node, right? So only backtracking allows us to move in the backward direction on the same path, right? From which we have traversed, right, in the forward direction. So from which point we have we have traversed in the forward direction. From that we can come to the backward direction, right? So start with the source vertex. We have started with the source vertex, that is A, right? Now I'll go from A, from the vertex A, right? From the vertex A, uh, I will go to the depth, right? I'll go to the vertex E, then I'll go to the vertex E. So I've covered it. I've covered the depth, the maximum depth till I can go, right? From here, right? Clear. Now source vertex was A, right? Source vertex are what A, and now we have covered A, C, and E. Now we will check it is B and G. Right? If there would have been any more vertex in the depth, then we could have checked it, right? So A traversal would be A, C, E, B, and D. So these were the few examples of BFS and DFS, right? One more thing I would like to tell you that it uses the two data structure to store the nodes we are visiting, vertices we are visiting, right? And it uses the stack. Why stack? Because we are using backtracking. Backtracking uses recursion, and that's why we have to use the stack, right? The complexity of both are bigger of V plus E. BFS and V is number of vertices, and A is edges. Like V is number of vertices and edges, right? Like, well, or you can also conclude with the fact that as uses the DFS uses stack, that we use LIFO application and approach is used by the Q is FIFO, so the BFS uses FIFO, right? BFS, and we also need to understand where to use BFS and where to use DFS, right? Like if we have to find the vertices, which if you have to find the vertices, right? You have to find the vertices which are closer or you can say nearer to the source vertex, then we have to use the BFS. And as the vertices are far away from the source vertex, then we have to use DFS, right? And we can say that BFS is used in so many graph applications, a bipected graph, shortest path. You can say DFS is used in this somewhere you can say a cyclic graph or something like, right? So these are the few things which we have seen about BFS and DFS. They both are the traversal, and now we will see the example also. We will see the Java implementation, right? Yes, wait a minute. So let's start with the coding part. So let's start on the program. Also, let's check this out. This okay. Let's note this one. This code is also right. If some of you are not getting the output, I'll fix this code. Don't worry. So let's start with a new code. We can say BFS DFS. Actually, there was some connectivity issue. We are again back. Let's start. Let's start again with the full fledged. Right. So now, where we are just having the, we just saw some examples of, we just saw some example of the BFS DFS. Now we will be implementing those program. We'll be implementing those program in Java itself, right? So let's see how we can make this program. So let's make a new program, new file. Like, graph type of selection. Let's. I made a file as class name with graph drivers. Let's. So we'll just make a file named this graph drivers. Right. The graph drivers. Right. We will see how we can make. How we can simply run this code. How we can simply traverse the vertices. Right. So let's start with the code. Right. So initially, simply like we have seen why how we have make how we can make basically how we can make the graph, how we have implemented it with the attention. Same way we need to understand how we will do this, right? Yeah. So let's implement this code with Java. So let me implement the same Java import Java dot io. I'll tell you what you can type also. Import Java dot beta. The same we have already implemented. As we have already declared the graph drivers. We have already taken the graph drivers. So what we are doing, we will traverse data, right? Let's move. We will return the variable as variable vertex, right? And we will also have a list, an adjacency list, right, to store the vertices also. That's also right. So I'm using the linked list, right? To make an adjacency list, right? So we are just linked list to, to create the adjacency list, right? So here we are basically we are creating, you can say, we are using this vertices, and we are creating this list. Just add agency, agency list. You can say agency list again, right? So that doesn't matter. I'm passing it the data type. It will not it will not a primitive one. Okay. We can define the integer class. That what kind of value we will be storing this agency list. Let's say the name is ADJ. ADJ is for the agency list of the vertices, right? Let's make a queue also. Why queue? Because we are using the queue for the BFS, because we are doing the BFS traversal. So I'm using the BFS. I'm using the queue for BFS traversal, right? Great. We are using the BFS for the traversal, right? So let's use this variable queue, right? So I'm having this I'm created a linked list which will be used for which will be used for the as a adjacency list, and I've already used a queue. I created a queue object QE, which will be used for storing the widgeted vertex while doing the BFS table, right? So let's make a constructor. So I'm making a constructor named this, and in this I'm passing the number of vertices, right? Right. In this I'm passing the number of vertices. So vertex, we have taken a vertex B. We can simply whatever vertex I will pass in this argument. So whatever vertex I will pass to the this, whatever vertex value I will pass to this parameter B, it will be stored in the vertex variable, which is stored in the total number of vertices. Now, as we have taken the adjacency list, so I will do, I will simply write ADJ, the adjacency list which we have used, right? So I will simply write ADJ list equals to new. So, what I'm doing, I'm just declaring the size over here, right? Yes. What I'm doing, I'm declaring size over here. See, the vertex is the total number of vertices which we get from the user, from the driver code. So the total number of vertices will be the size of the this linked list, right? This linked list, this basically this adjacency list, you can say, right? So what I'm doing, we are just iterating. We are just basically what we are just iterating to the language in list, right? So we will run a loop from starting of zero, then we'll go to the this, right? To the V. So I'm using this concept. Right? each list with this is a equals to new every time new node list, right? So I'm simply writing simply taking adjacent list I equal to then we are declaring this as a new linked list. So we are having this basically we are iterating through the vertices, right? All the vertices we have been saying we are having in the adjacent list actually, right? So now as we are saying, so we have just initiated all those lists and we are just passing the vertices to the list queue variable. You now say suppose let's again make a method so that we can insert the edges, right? Void insert. So let's make an insert edge method in which we can insert the vertex, right? Right. So basically what we are doing, we are inserting the edge to the adjacency list. How we will do this? Simply write 8gj, we add the vertex dot add. So we just with the add method, we are just adding the vertices to the adjacency list, right? So this insert edge is what is doing. It's inserting the edge from this V to W, from V vertex to W vertex. We are adding the edge, right? Right. So whatever we are adding from adjacent, basically adjacent vertex V and then adjacent one W, adjacent vertex W. We are just creating an edge, right? We're just inserting an edge, right? Right. So this is what we done. Now again, will be called. Let's make a function as BFS, which will actually do the traversal, and I will pass. Let me mention the number of edges and click. And I will also explain that. And see one more thing. Remember that we are considering the edges. Considering the edges, you can switch into the right, adding right, adding the edge. You can say to adjacent list and considering. We are considering that this is bidirectional. Okay. Now let's jump back to the BFS function. So I've taken a BFS method, which will be like which will use for actual traversal. So I'm making and I'm taking a boolean variable and I'm taking array which will be stored, which will be an array named as nodes, which will be checking whether nodes are visited or not, right? So equals to new. Right. So first we have declared an array named as nodes, right? and I'm taking a variable initializing with the 0. Why? So that I can check I don't count basically. So by default I'll just declare as true and initializing true. Now I'll add the root node to the queue. How will I add? To variable dot add queue is also simply add with this. So what I'm doing, I'm just simply adding the root node, right? I simply added the root node, right? Adding root node you can see in right and the root node to the queue, okay? To the queue. Right? We are adding a root node to the queue. Right? Okay. So simply what we are doing, we are just simply added the root node to the queue. Right? Now until we will run a loop until the size of the queue becomes 0. So I will write while queue dot size method I will use is not uh, 0. While queue dot size is not equal to 0, we will run a loop. Clear? Clear? So I'll run a loop and equals to queue dot poll. So I've used this poll method so that I can remove the top element of the queue, right? I can remove the top element of the queue, right? The poll is a queue function to remove the element. So I'm removing the top element of the queue. Top element of the queue. Yeah. Okay. And queue dot poll to remove the top element of the queue. So we use this method, right? Now the element which now suppose so we have removed the top element here. Now I will print here, right? System dot out dot see we have, whatever element we have removed, the value will be stored in the end. So I'm printing the element which I have removed, right? So what is printing the so So inside this, I'll run a loop. I'll run a loop. Why? For int I equals to 0. And now what I'm doing? I'm just now iterate through the linked list and I will push all the neighbors in the breadth first search. What we do, we visit the neighbors vertices. So I'll just iterate through the linked list and I'll push all the neighbor node into the queue. So how will I do this? For this, I will start a loop from 0. Right? I less than and density is and node vertices dot size plus 0, right? A is the variable, initial variable. A equals to 1, 2, 3, that we are getting the vertices from, as we are iterating to the list, we are getting the vertices and storing the A. Right now, again, I will check if I simply write if there are no nodes, if there are no nodes, if the nodes are not there. Right? If it is the case, then I simply can we just only have to only insert. Then if it is the case, then I only insert nodes into queue. Right. So now let's see. If this is the case, then what I'll do, I'll simply write if the nodes are there, if the nodes is not visited, then I will simply add in the queue entry. I will insert node into the queue and I will simply perform the add function and then let's simply I'll close this for, I'll close this while, and I'll just close this method. Done. Now let's immediately again start the main method. Right. And let's craft table. So we've taken the craft table. So let's say that G equals to name. Let's pass the number of vertices 8. So the pass number of matrices is 8. See, remember, you remember that we have taken constructor and in which we are passing the number of vertices. So here I'm passing the value as 8. We can pass any value whatever you want, right? So G dot, now I will insert the edge. I insert edge from 0 to 1. Let's see. Just pass it 10 vertex. That would be better. Right, so you can change any number. 2, 3 you can say, and 1, 2, 3. And 2 to 4, let's say. You can write any value. You can write any value. You have to write. You can simply, you can write any value, right? I'm just taking the random values. 5, 2, let's say 6, 5. 7, right? Team 19 and 100. Just a second. 16. Wait. Okay, sorry. Zero will come here, so here also I made a three. Wait, wait. Today I have some issue in my interpreter, so let me set this so that we can see the output also. That means I will just program as I am having some issue today. Compare a bit. This program first so that I can check because my like application has having some issue today. We're getting the correct program. Just that we had little bit output issues there. Don't worry, I'll make this all working correct. Okay. So now like we have very less time. Let's jump to the next part. Okay, then now let's make the working with the program. As you already see that how DFS works, let's see this in Java itself. So let's make a DFS program also. Like this is a again we have taken a graph class as graph drivers, right? After moving flag, we have taken a variable private int variable vertex. You can see when we have declared private int variable adjacent, right? Adjacent list we have already declared. We have used an notation also, right? So I'm using this. Okay. Yes. Great. But this is a class of a graph. Driver is class is a private int v. We have already taken that again a variable private. Same variable I can use over here. And then let's say linked list. Right. Linked list looks like adjacent areas. It is right. Private int we have taken. Here we don't need to use a stack queue because in the DFS we don't use the queue. Right. Now let's make this concept the public. That's in which we are passing the vertices, and vertex equals to v, right? The vertex which we have used, private int vertex, yes. Naming this in which we are passing the vertex. It is the v vertex we have taken. For I will then move from I0 to I by same procedure. That the only the two things will be changed from BFS to BFS, right? Now we are making a program of BFS, right? So starting with 0, then we'll return to the V, recommend the loop, right? Then I'll add this vertices into the loading list. Right? And now I'll add this. We have done this. New addition, we have list the new list, and then we don't use this because we are not using any key over here. We run the for loop. For loop, we are just adding the values in the new list, right? And we are add edge or insert edge. You can see the same method. Insert edge, then we are passing to vertex v and w, right? Right. So we have just passed this value vertex also there, and we have just added the now we have just add we will be just adding the vertex to the list, right? Okay. So this is let's pass this vertex. Right. Let's take multiple as boolean nodes, right? The nodes boolean nodes will be there. You can simply write this also. You can simply declare this. And you can write here also. You simply write here also nodes equals to you. Let's int n. Here we have to use the int n, right? and we can show any vertex also there. And instead of and so that we don't get confused, it says vertex so that you can remember, right? Vertex is different. Let's make it that one get confused. Let's just fix it so that we don't get confused. Let's declare the variable as b, and then we have declared identity list, and we have passed. Right? Right? And then we are going to insert the edge, add edge, dw, add b, w, right? And let's send this over to DFS program int b, and vertex, let's say vertex variable a equal to 0, is execution, and let's say node vertex equals to true, q dot and we don't want the q because we are not using q here. So what we declare the nodes that is q that we take a variable, right? So let's print the number of the number of vertices over here. So vertex, let's print the number of vertex, right? We don't need this. So I'll run a loop for, right, for I equal to 0. I'll tell the vertex size plus, right? I'll run a loop from 0 starting to the adjacent vertex, adjacent list, adjacent matrix size, right? Or whatever vertices it is having. I'll run the loop from starting to the size of the vertices, total number of vertices, and I'll iterate to this. Then I'll get, right. Run out some name there, right? The question set. What I'll do again, I'll call it. What I'll do call BFS function. Again, I'll call BFS function. I will pass a and a and no, right? So again, this is basically the point of the question. Right? So passing a and the nodes. If our nodes are not there, right? This is closed. For loop is closed. For that I already written, and I'm checking whether nodes are not there. Nodes are not there, and I'll again call the DFS, right? So we have done this. We have done, right? So we are done with this. This is closed. For is closed. Right now, let's again make a function, right? So now we will store all the nodes which we have visited, right? So you can say DFS visit. Let's say DFS visit, right? DFS. You can simply write this DFS and this is DFS until because you will not visit until, you can write this as visit until so that you will not confuse. Here I'm taking the DFS. So here I'm inserting all the vertices which, right? So here I will take Boolean variable already. Though I'm taking a storing basically. I'm just already there's this already array which will store in the Boolean variable whether the vertices have visited or not. So I'm just maintaining an array which is keeping the track whether which vertices are visited or not. Right? Okay, so new and then again I'll call. I'll pass v comma or the array of. I should write that first traversal is okay. Wait. See, here are getting the output. That first traversal is this 0, 1, 3, 5, 2, 4, 7, 8, 6. This is the answer. This is the answer of this is that first traversal, right? Here we are getting is so here we are dealing with that first traversal from 0, starting from the 0, then 1, then 3, 5, 2. Because from 0 to we are going to 1, then we are going to 3, then we are going to 5, then we are going to 2, right? Then we are going to 4, 7, 8, 6, right? This is how we are finding the depth of traversal. Or you can also draw the graph and then you can finally see how we can draw this, right? Okay, so this is what we have done during traversal, right? Okay. Thank you so much for the part. Now I'm again taking a small session for you can say dynamic programming, right? Let's start the dynamic programming also. Let's start the topic. Let's start the topic dynamic programming. What dynamic programming is and how do we understand this, right? So it's very important to understand the dynamic programming nowadays because like so many things we understand, so many things we get, so many times we heard about this term dynamic programming, right? So let's start to understand what basically dynamic programming is. Right? Right? So dynamic programming we can say I can simply write in the terms of dynamic programming, I can simply write that it divides the you can say it divides the a problem into series of overlapping sub problems. Now you can say simply straight away that sir, that you are saying that a dynamic programming is one in which we divide the problem into a series of overlapping sub problems. But the only thing is that why it is different from the divide and conquer. Why? Because in the divide and conquer, each time you divide into sub problems which are not overlapping actually. But in this, what we are doing, we are dividing a problem into sub problems which are overlapping. Overlapping means some of the sub problems have the common. Some of the sub problems are there whose solution is already there. What we do, we just store the solution of those sub problems into the tables. So whenever we get the same sub problem, then we can simply take the solution from the table itself. By instead of solving, we can just quickly get the solution from the table, right? Don't worry, I'll take the example table for example. I'll take the example also, don't worry. Right. So there are two features, you can say there are two features, I would say. There are two features, you can say, of dynamic programming. You can say DP. First one is the optimal substructure. Optimal substructure. The second one is the overlapping subproblems. These are the two main factors about the dynamic programming. That first one is the optimal substructure. That you say is, sir, we always find, now the question comes, sir, we always find optimal solution in case of greedy algorithm also. Yesterday we saw that we find the optimal solution, but it is not the case here. That that the greedy approach or dynamic programming approach is same. Why? I will tell you, don't worry. Right? I will tell you, don't worry, how it is different from the others. Right? So, for example, in the greedy also we find the optimal subsolution, and in the dynamic and programming also we find the optimal substructure solution. Right? Right. So how it is different from the greedy? Let's say, for example, we have two paths: source, two vertices, source and destination. Right. So for source, these are the three ways. So, so now this is also, so So let's consider this scenario. We have to reach from source to destination. Let's consider this scenario. So we have to reach from source to destination, and we have three ways, right? So while looking at the greedy solution, while looking at the greedy approach, I have to choose the minimum weighted path. I have to choose the minimum weighted path. So by looking at the current situation, right, I will choose by this. I will choose this with the help of greedy, right? Because but in future, suppose let's say it is 10, it is 20, and it is 100, 5, 3, 1. But in the future, it is not the optimal. But in a sub dynamic programming, we always we always tend to try the best optimal solution with the help of optimal substructure, right? Right. So, for example, I can choose this way, 10, 10, 10. So this will be the optimal sub solution for me, right? But greedy also find the optimal solution, but in the greedy, this is not the case that every time you get the optimal solution, right? This is the basic funda about the optimal solution, right? So now let me tell you, and let me explain one more thing, that basically in the divide and conquer, you divide each and every problem, right? You divide each and every problem, right? Each and every problem. So in each and every problem, you solve it individually and combine the solution. But in the dynamic programming, what you do, you divide the problem into sub problems, and you store the solutions of the sub problems also, so in the table. So once again in the future you get the same sub problem, so just quickly replace retrieve, you quickly access the solution from those tables, right? This is what about the dynamic programming. Let me take in one more example with the help of Fibonacci series also, right? So let's say how while we write the Fibonacci series is what function of n is equal to every term in the Fibonacci series is the sum of last two terms. है ना? For example, one is for n equal to for first term and zero for so the zero term will be zero. The first sorry, so first term will be zero, right? Right. First term will be zero and the second term will be one. I'm just stating this, right? F of n minus one equal to any term in the Fibonacci series f of n minus one plus f of n minus two, right? It will be one if n is equal to one. It will be one if n is equal to one, right? So what I'm just saying f of one and f of zero, the first term would be zero, right? We know that. Now we need to understand this by the example like this: n equal to 0, 1, 2, 3, 4, 5. N is the terms and zero term, first term, these are the terms. Zero. F of n is what? 0, 1, 1, 2, 3, 5, 8, 13, like this so on, right? Clear? Clear? Now, these are the terms of the Fibonacci series, right? F n is 0, the F n and n will be written like this. Right? So, suppose, suppose f of x is there, f of 4 is there, f of 4 is there, f of 4 is what? F of 3 and f of 2. F of 3 is what? F of 2, f of 1. I'm dividing the, so this is the optimal substructure, right? I'm dividing the problem into subproblems, right? F of 2 is what? F of 1 and f of 0. F of 2 is what? F of 1 again, f of 1 and f of 0, and so on, right? And so on. Now, now I will be maintaining a table, right? For solution of what is the value of f of 2, f of 1, f of 0, f of 3. So instead of solving these individually, instead of solving this, because see, the fourth term is what 2, and it is made of this is f of 0, f of 1, f of 2, f of 3. So I'm storing the value of these values. I'm storing f of what is the value of 0, what is the value of f1, what is the value of f2, what is the value of 3. So I'm storing all this procedure, all these values in a table. So whenever quickly read those values, I simply quick from get from here. What is the value of f3? Value of f3 is 2. The value of f2 is 1. So 2 plus 1, the third term. Yeah, I got the answer. This is how exactly the dynamic programming also works, right? Maintaining the optimal substructure, right? And it has the overlapping subproblems. How? Let me tell you. F of 2 is already there. F of 2 is f of 1 already there, and f of 1 0 is already there. So it has the overlapping subproblems. It has the overlapping subproblems. That is how you make this table, and that is how you solve this, right? Clear? So now let's sum up this session till now here only. Now I would request all of you to please ask your doubt if you have any, right? And simply put your doubts in the comment section, right? And you can take a screenshot also of the same. And simply take the screenshot. So you simply put your comment in the comment box and just simply ask your doubt, right? I'm waiting. You can simply straight away ask your doubts in the comment section. You can ask a doubt here so that I can answer you. All the students who are there, you can just simply ask the doubts. Right? Any doubt, anyone? Oh, sorry.